and my annotation disappeared because I forgot I had to reshare the screen. But here's where we're at so far. We're in section 13.2. We only just barely opened it up and started talking about the conditions. We haven't actually done a first example yet, but we're going to look into a couple examples of verifying conditions of our new statistical method that we're about to discuss in section 13.3. But because this is the goal, let's take a look at it just as a peek. We might be getting into these notes today. This is what the full procedure is going to look like. To do a confidence interval, we take the statistic p hat, we add and subtract a specific number called the critical number, z star. We even have a table lookup that corresponds to different confidence levels to say what the number is. At 95% confidence, it's a 1.96, which was pretty close to what we did in section 13.1 when we multiplied by and subtracted by the 2. So what we did in this section was essentially the confidence interval. We took p hat plus or minus an approximate critical number, not quite the right value, but very close, multiplied by the standard error, and that's the whole procedure. Lots of stuff goes into explaining how and why it works. So that was what 13.1 was really all about, talking about sampling distributions, how the normal distribution came into play. But there's also a lot of discussion in what are the conditions to ensure it works as well. And that's what 13.2 is all about. So we'll come back to this formula once we're in section 13.3 specifically. And for now, we're going to talk about the conditions of that particular confidence interval procedure in 13.2. But other things just as a reminder, quiz 7 is due today. This one's based off the chapter 7 regression problem. And quiz number 8 is now officially assigned. I'm posting these on Wednesday just because my Thursdays are pretty busy. Quiz number 8 is highly based off chapter 10. So take a look at the things we did in chapter 10, experimental design versus observational study, statistic versus parameter. And those are the kinds of things coming up in quiz 8. The big thing in quiz 8 is determining what conclusion you can make. So look for the part of the notes that discusses only a bona fide experimental design can allow you to make a conclusion that has anything to do with cause and effect. So that's a big part of the quiz as well. So we're about to take another look into 13.2. Any questions at all, folks, before we jump back in? Okay, so let's take a look. So 13.2, we started by just restating the central limit theorem. The big takeaway from the central limit theorem is we changed the standard deviation into the standard error. So we'll calculate that a couple times on these notes as well, just as a reminder that these are the assumptions and conditions that allows this confidence interval problem to really work as intended, to allow our conclusion to actually make sense and be accurate. The independence is the hard thing to check, but the things that we can check from the write-up of the problem will be the randomization. We're looking for some level of randomization. We're going to see if the 10% condition is met. Our sample, we like it to be large, but this is the counterintuitive thing about statistics. If it's too large, independence is violated in a different kind of abstract way. The central limit theorem starts to break down. This becomes not true any longer, that the things are approximately normally distributed. So the thing we check is 10 times n should be less than the sample size, which we designate as the uppercase N there. Finally, the success failure condition is not too bad to check. In order to get an accurate normal distribution, we also require a large enough sample size so there's at least 10 successes and at least 10 failures in the sample. So putting this all together, here's our generic example 1. Full disclosure, this one's a made-up problem, but I didn't want context to get too crazy when we're learning all these different parts for the conditions of the test. So it's kind of a simplified situation. It goes on to say, to start the context, researchers in the development of new treatments for cancer patients often evaluate the effectiveness of new therapies by reporting the proportion of patients who survived for a specified period of time after the completion of the treatment. So it's kind of morbid data when you really think about it. We're looking at survival time. And one good benchmark for survival is surviving at least 5 years after treatment. So cancer sucks and it's awful, and this is a pretty realistic setting at least. It goes on to say this is a fully made up part of the problem. A new genetic treatment involving a simple random sample of 25 patients with one particular type of cancer. Maybe it's melanoma, or maybe it's some kind of bone cancer. There's like loads of kinds of cancers altogether. But for this particular new treatment, they had a result of 8 patients surviving at least 5 years after treatment. Well, to really check the conditions, we have to really think about that context hard. You have to know what the sample size is. There's a bunch of numbers, but 5 years after treatment, that was just part of the context. 8 patients surviving isn't the sample size. It would be indicated here when it said random sample of 25 patients. That gives us a sample size of n, 25 in this problem. But the next thing we need to know for sure is, what would you all say is the success in this situation?
It's gonna be something around patients that survived when we started it.
Yeah, exactly. Surviving at least 5 years after treatment, this is what they're talking about as a success in this problem. It's a thing that seems to be like the drive of the study. Usually it's mentioned more than once in the context. It also says here, new therapies are evaluated by reporting the proportion of patients who survived a specified period of time after the treatment. So that seems to be the drive of the study. The success is what the study is really interested in studying fundamentally. And when it says 8 patients surviving 5 years after treatment, that's telling us altogether there are 8 successes. But that doesn't answer part A. Part A wants to know what is the success in context. So we have to say a success is surviving at least 5 years after. It said it was a new genetic treatment, so I'll just say after the new treatment. Again, it's okay to make the context a little bit more summarized when you go to write it down here. You don't have to mention every element. If you said the new genetic treatment, that'd be great as well. But if you shortened it up just a little bit like we did here, you're still involving the context. So we got the context in when we said surviving at least 5 years after the new treatment. If we were talking about the population, we would have said the population would be all patients who have this specific kind of cancer, whichever kind of cancer it was. They never told us in this made-up context either. But the major reason why this is kind of a simplified problem is we want to study the conditions altogether and see how they relate to this kind of problem. So when the context does get a little bit more hairy, we can see how this all goes. So it says in part B, determine if the assumptions and conditions of the central limit theorem are met. That's these 4 assumptions right here. But the ones we'll specifically check as a quiz problem or an exam problem would be conditions 2, 3, and 4. We can't be sure on the independence assumption, but if everything goes right, it's reasonable to assume that it is true. Under rare conditions, even when conditions 2, 3, and 4 are satisfied, you can violate independence. But the only way to know for sure that that happened is you have to be part of the research group conducting the study to know exactly what's going on. And our write-ups are pretty short, so we're just to do the best we can with the information we're given. So independence says the individuals in the sample must be independent from one another. That seems reasonable here, in all honesty. If we're talking about a new treatment for cancer, someone's survival rate is probably not influencing someone else's if they're 25 randomly selected people. Is that true always? It's debatable. What if, say, 5 people in this study just formed a group and then they do the same things all the time? They eat breakfast together, they go to the same yoga classes together, they're living very similar lifestyles, all of a sudden their survival rate might be somewhat influenced by each other if they're all doing the same kind of thing. Independence is violated in that case. And so that's in the way in which these things get really complicated as studies. It's not like we don't want the patients to interact with each other, but the more they do, the less independence looks like it really happened. Well, here's what we can check. We look through the context again and see if they mention something about random. We just wrote in the problem. It was a simple random sample. So we'll say here for condition 2, the sample is stated to be a simple random sample. So that condition is met. The condition is met. Let me take a quick screenshot so we're not scrolling up and down a bunch. So with that condition being met, we'd move on to the second condition, the 10% condition. Here's where it gets a little bit vague. We know the sample size, let's take a look, was 25 patients altogether. And the way we use the 10% condition is we multiply that sample size by 10. So let's use that same exact formula. 10 times n, lowercase n is going to give us 10 times 25, which is going to be 250 patients with this cancer. Now, is this condition met? We have no clue. The context didn't even tell us what kind of cancer it was. If this is a common cancer, say like melanoma, this condition is probably met. 250 patients is nowhere near 10% of everyone who has the cancer melanoma. That's a pretty common one that afflicts a lot of people in the United States alone. The population size is way over 250. But cancers are pretty weird and unusual. There's plenty of forms of weird cancer. Any part of your body can become cancerous at any time. And so if this is one of those extremely, really rare cancers, there might be less than 250 people that we know of that has it. In this case, the 10% condition is just not met. So condition checking is hard. We have to go based off of what we're giving in the context. We're not given a lot. We're just told this was a particular type of cancer. So we have to make a judgment call. I can't tell you for sure if this condition's met or not, but we can still discuss it at least. We can say, assuming, I'm going to put in an extra assumption here, assuming this is not a very rare cancer. This is assuming more than 250 people have this particular kind of cancer. This condition is met. I think it's reasonable. It's probably met because if we're looking into a new genetic treatment, we also know that cancer treatments usually are targeting the cancers that are a little bit more common, especially if it's a really fancy treatment. They go for the ones that show up the most to help the most amount of people at one time. So it's probably a safe assumption that it's not the world's most rarest cancer. This one's kind of common. And if that's the case, this condition would be met. But I'm putting in my own assumptions into this problem. We don't know exactly what the cancer was. We just try to answer the question as best we can. So anything you say here that's talking about the context, talking about the 250 as it relates to the population, you would get full credit for this if you argued either way. Said anything that's reasonable with the context. It's all just about thinking about this condition. This is something that they would have thought about as well before they designed the study. They would have said exactly who the population is, and they probably would have taken a sample that wouldn't have violated that in the first place. But it's up to us to check the condition, just to think about how they work. And so I'd say that would be a common thing to say for this problem, going off pretty minimal information. Well, any questions at the moment, folks, with the third condition? Okay, condition 4 is tricky because it has a particular formula that goes along with it. But here's what's weird about this. We don't always use the formula unless the data is just given us in a particular way. If the data gave us a p-hat value, then this is a good formula to use. But there was no percentage of successes in the sample given to us. So we're just going to use the part that's highlighted in gray. Count the successes in the sample and the failures that has to exceed 10. The sample size itself is 25, but when we go up to the problem again and look at the context, a success is surviving at least 5 years. We're told only 8 patients survived at least 5 years after the treatment. There's not actually enough successes here for the conditions to be met. So the success failure condition fails on this one. We can write out there is only 8 successes, which is less than, we know 8 is less than 10, but saying this is just a reminder, it's less than the 10 successes needed. This means for this one particular part 4, the conditions are not met overall. We can't actually use the central limit theorem overall on this one. We're going to get a normal distribution curve that's oddly shaped, probably skewed, or even worse. And even if everything goes right, even if the randomization was perfect, that the sample wasn't too large, that independence was flawless in this particular design, if we don't have enough successes in the sample, then central limit theorem is inaccurate, and our confidence interval procedure would be inaccurate as well. Doesn't mean the study is ruined, though. Turns out the world of statistical inference is really vast. There are hundreds of statistical methods. We just like this one. This is an easy one to discuss in a class. It's a decently powerful method, but if its conditions fail, we'll go to the next statistical method. Maybe its power is a little bit less, but we can still say something about the data. But that's what condition checking looks like for these kinds of problems. There's a lot to say and think about for these, so we'll try another problem before we go on to the next notes and look at the full procedure. I think there's a little bit more to this as well. Let's go on to the standard error next. Any questions so far at the moment? Okay, last thing it asks us to calculate is the standard error. This is really kind of just practice for us at the moment. We're going to need to compute the standard error when we do the full confidence interval procedure. And here's how it goes. When you see the word standard error, the symbol would be SC p hat. If you didn't write that down, it's not a big deal, but this is the symbol that comes up that ties in the definition. The thing you should definitely write down is this formula. P hat times 1 minus p hat, divide by the sample size n. If you didn't write down the formula, but you got the right number, that's no big deal either. But writing it down is a good strategy as well. If you ran out of time on an exam, but I saw the formula is correct, that's worth some partial credit just on its own. Maybe not a lot, but some is better than none. But writing down the formula also tells you what the next step should be. You have to actually calculate p hat itself. P hat is going to be the number of successes divided by the sample size. The sample size is n, so this is going to be something divided by 25. But we have here just listed out, there's 8 successes in the sample. So p hat is h divided by n. Actually, let's say it this way. Number of successes, which then turns into h divided by 25. We're rounding our end answer to 4 decimal places. So let's take 8 divide by 25. This one's kind of nice. We get a 0.32. So now we can calculate the standard error. Any questions first on getting these two parts here? The formula, then the 0.32? Okay, putting this all together, the standard error for p hat is going to be the square root of, now we're just dropping in values, kind of like using the 1.5 IQ rule of thumb, or doing something in chapter 7 with regression with the a and b values for slope and y-intercept. It's just another formula, so another set of substitutions. In place of p hat, go 0.332, then 1 minus p hat again here, 0.32. And the denominator is the sample size, but that's just at 25. So we toss all this into the calculator, and here's what we're going to get. Hit second, power 2 button up here on the left, pulls out the square root, then just write in the numerator, 0.32. We made a big comment yesterday. You definitely need the parentheses because it would be an order of operations error otherwise. 1 minus 0.32. And sure, we could take the subtraction 1 minus 0.32 and put something like 0.68 there. But for me personally, I wouldn't want to make an error on arithmetic just by accident. It's probably just convenient to type it in verbatim and be just extra sure about the answer. Divide by 25. And to 4 decimal places in rounding, this is a 0.0933. This one rounds up. 0.0933. Does that look right to folks so far? Awesome. So if the conditions were met, we could move forward. We could actually compute the confidence interval, which would tell us the population proportion of people who would survive at least 5 years after this particular new treatment, whatever it is. But the conditions were not met, so we would have to actually stop right here. We compute standard error just for the sake of practice, but this problem would require some different kind of statistical method, and there are others out there that could handle data like this. Well, the major thing is about assumptions and conditions, so we'll try this out again on another problem. Any last questions at all, folks, on running through that first example? Yeah. The number 3 right here? Yeah, absolutely. The logic on this one is honestly pretty tricky in a way. Let me put this here just as a quick reference. So focusing on 3, the 10% condition, the best way to think about what we did there was the statement says our samples should not exceed 10% of the population. Yet we're looking at 250 patients, so that's pretty weird in a way. But what we did was we wrote down this equation. When we say our sample, we're referring to the lowercase n, the sample size. Uppercase N is the population size. So 10% of the population would just be 0.10 n. So this whole statement here turned into the one that's highlighted in yellow down below. Then the next thing we did was we just multiplied the left side by 10, the right-hand side by 10, and it becomes this rule. So the big punchline is that to make sure your sample does not exceed 10% of the population, you just have to argue that 10 times n is less than uppercase N, where this is the population size. So our problem had a sample size of n is 25. That means we took 10 times n, it got 250. And so that would mean we're looking at 250 right here. Yeah, go ahead. That's a good point. I think the more typical problems is kind of an unknown population, kind of like this one here. Yeah, exactly. Sometimes the assumption is really vague, like in this one. This one's hard to tell. Other times, it's more like, say, this one, where you have kind of immediate assumption the population is probably really large, because this is one for all infants. So yeah, for a real exam problem, I don't think I'm going to make it kind of uncertain, like on this one, where that really just depends on the kind of cancer we're dealing with in the very first place. That would make it kind of an uncomfortable exam question. But once we got that 250, here's where it became that kind of tricky question. 250 is the patients with the cancer, and is the population size, everyone with the cancer. And we don't know what the cancer was. It just said 25 patients with a particular cancer. So if it's rare, the condition's not met. But if we assume that this is a cancer that is pretty common, like melanoma, then we can say 250 patients is not more than the population size, uppercase N up here. And so if this is not a very rare cancer, we said the condition's met. 10 times the sample size isn't larger than the population size. But does that help to see what was going on here with the logic on this one? Yeah, that's the same question that you were mentioning as well. The population is a big unknown on this one. But you know what's kind of crazy is the population kind of is known on this one. I didn't expect this question to come up, but I was just kind of curious myself on this one. This is kind of a, sorry, go ahead.
The 10%, it says our sample should not exceed 10% of the population.
Yeah,
Is that true?
yes.
So like if above the sample was 250, if the sample was only 2,000, or if the population was only 2,000, then it would not meet that, correct?
Well, what we took 10 times on N was the sample size N itself. So the N was the 25 right here.
But say you were given the population.
Yeah.
You could find it out, and it was only 2,000.
So if N was 2,000, then our condition would be met down here. Because the 250, that'd be the 10 times N, would have been less than the 2,000 that would have gone right here.
Why does it say 10% of the population? Our sample should not exceed 10% of the population.
Gotcha. So yeah, that's the tricky thing about this times 10 rule right here. So if the sample size is 200 and we had a sample size of say 25, we'd have had 25 divided by 2,000 going like that times 100. And we would have been at just barely above 1% of the population.
Gotcha. I'm with you now. Thank you for explaining that.
Gotcha. Yeah, absolutely. So this one's really weird because we took this entire line, which became this inequality. Then we turned it into this one, which meant we took 10 times the sample size to get that 250 out. But other questions at the moment about that? No, that's a good question to mention. And again, that's kind of what everyone's question is about this. How do we check the 10% condition when we don't even know the population size? In this problem, it's extremely vague what the population size would even be. And then at the same exact time, the way we're checking the condition, taking 10 times the sample size, is kind of vague itself. Does it make sense on why we're doing the times 10?
Yeah, now it does.
Awesome, glad to hear that. To me, when I was looking at these notes just Monday, that was the thing I had to refresh on myself. Why is it times 10 again? What I do is I look at my old notes that I did in 2024, back when we had Moodle, and I saw the 10 times N there, and I didn't really see how I got that on my notes. So I had to reverse engineer it, and I finally worked out it came from this right here. I wish I had put it in my notes because it was confusing to me when I read it again. But the sample size of 2,000, again, we're not sure on this problem. The problem down below here is a little bit vague, but we can actually kind of investigate a little bit on this one. So let's work hard on the population size for this. The population is going to be all infants, but we don't mean all infants on the planet. We mean all infants in 1974, but again, not all infants on the planet in 1974 either. The Lancet is a British journal. So this was in Great Britain. In Great Britain in 1974, there was a controversy about vaccines. It seems like there's always a controversy about them. They were worried about the whooping cough vaccine causing some pretty nasty reactions in some kids. So they gave infants, 339 of them, a random sample across the country of Great Britain, the injection, and they tracked them and saw how many of them had a reverse reaction to study this. So this was an interesting thing in for its time. But what this tells us is, I did a little research personally. In 1974, Great Britain had, it was, let's see here, a population of 56.2 million. So that was everybody in Great Britain. And the other piece of research I found, which was interesting, was we also know the birth rate. The birth rate in 1974 was 13.1 per 1,000 people. So now you can combine these two pieces of data. I'm making one big assumption that the infants are 1 year old or less. I'm not completely sure about that, but if I make that assumption, I'm talking about even a smaller population size. And the smaller it gets, the closer it gets to not meeting the condition. So we're kind of estimating in a conservative way. I'm checking, is this going to fail? Is the sample size too large? I'm going to look into the population of all infants less than 1 year old in 1974 by combining those two pieces of data, the birth rate and the population size. So the number of infants less than or equal to 1 year old in 1974, keep getting those numbers mixed up, 74 in Great Britain is approximately, and this is our population size, uppercase N. So take 56.2 million. That's an approximation too, but we're doing the best we can with very minimal information once again. So 56, 200, 000, 56.2 million. Multiply it by the birth rate. That's 13.1 per 1,000. So that means you take 13.1 divided by 1,000 to get the number 0.0131. So we're combining this information here and this other information right here. And we get the number, well, the approximate number of infants less than or equal to a year old. So 56, 200, 000 times 0.0131 gives us a total population size of infants in Great Britain at this time of 736,220 infants. And we could have researched even further. We could have said, who gets the whooping cough vaccine? When in the kid's life do they get it? Is it less than a year old? Then this would be a pretty well targeted sample size, but I'm really not sure on that. I don't know if this is something you get as a 3-year-old more typically these days or in 1974. But this was a way to find out the population size of less than 1 year old infants, about 736,220. That tells us that our 339 infants, nowhere near exceeding 10% of the population. We can take 339, divide by 736,220, and get the percentage. It's using scientific notation, and so that's a dead giveaway. It's a small number. Or you can take 339, multiply it by 10. This cannot be larger than the population size. of 736,000 approximately. But you know, the big takeaway about all this kind of stuff is you never have to do that in this class. The context they give you is sometimes pretty minimal. This wasn't a lot. We've seen this problem before, and now we're just investigating it further. So just use what you can assume by the problem that's given, and you're always doing this just right. If you want to go the extra mile, you can investigate further, do your own research. I would encourage you not to pay any money to buy the journal just so that you could read the article. Sometimes these things are behind paywalls and you can't even read the whole thing, unfortunately. But if you really want to know, this is some of the ways you can actually get the population size and finally nail down that number. It's an estimate, it's kind of a crude one, but it gives us something to work with. But any questions about the population size on this one, just to have a number to work with? Okay, so the big takeaway is, again, you don't necessarily have to do that every time. When it comes to the 10% condition, just use what you know. If it's talking about infants, probably we're talking about a lot of them. If we take 10 times this number, 3390, the population size is very likely bigger than that. Unless for some weird reason, the population was everybody in Rigby in 1974. We might be in trouble then. I think that's probably a smaller population. But let's work through the problem again. The major thing is to check if all these conditions are met. But the first thing we need to do is determine what is a success in the first place. We have 339 infants, so that's the sample size. N is 339 infants. This is evaluating the policy of vaccination in infants for whooping cough. And we're told adverse reactions were monitored in 339 infants. So it's talking about adverse reactions once, and that makes us think that's probably what the successes are all about in this problem. It goes on to say reactions, as in the adverse ones, were noted in 20.35% of the infants. So that word came up twice, and they're talking about adverse reactions twice, really. That's what the study is all about. How many of these kids had a bad time after their first injection of the whooping cough vaccine? So that's the success. And sometimes this sounds pretty morbid, and the last problem of success was a good thing, survival time. And this one will say, even though it sounds like we're being a monster, a success is the infant having an adverse reaction to this vaccine. And you can be more specific by saying the whooping cough vaccine, but that's a big part of the context. If you just say that this vaccine, everyone would know what you're talking about in this problem. So we have the context mentioned. We know what the success is, but we don't actually know the number of successes. We know something else. 20.35% were reactions noted of the infants. When they say of the infants, they're talking about the 339, the sample, in other words. So in this particular problem, they actually just straight out gave us p hat is 0.2035 as a decimal number. Recall, when you use p hat in a formula, you want the decimal as opposed to the percentage. So we've got the successes down. We have two elements, the sample size and the proportion of successes in the sample, the p hat value. Now we're going to run through the assumptions and conditions in the essential limit theorem, the big last three, and see if the conditions are met this time. But any questions at the moment with part A? Okay, let me see if I still have that screenshot. There it is. Here's our conditions. And notice what's missing right away. These write-ups are really brief. When you open a journal and read an article, you are often presented with an abstract, and the abstract tends to have more than what we have here. This is like a very, very cut down minimal abstract to make it a textbook kind of problem. And it makes sense. We can't read an entire journal or a big long abstract on every single statistical problem we do. or else we'd be getting bogged down with context and losing the concepts. So we just do the best we can with the information we have. But there's nothing here talking about randomization, not even once or even hinting at it. You might assume it was a random study because it was published in a well-known journal, a reputable one. But if we're going by the information given us, this is what I would say with part two. It is not known by the given information, what was written in the problem, if the sample is random, let alone if it was a simple random sample, which is the gold star for randomization. We don't know by what we were given at all if it was even random in the very first place. Doesn't mean conditions overall failed to be met. It just means this is something we can't check either. Just like I can't tell you what's going on with the independence assumption. Probably independence was met on this. I can't say how adverse reaction on one child is going to affect the other, unless the children are mirroring each other for attention. Who knows? If you put children together in large groups, anything could happen. And same with randomization. I just don't know here if randomization's met or not. We can't check it based upon given information. So this isn't a fail. This is a total unknown. We don't know if it succeeded or failed by the write-up. My inclination is it was random, but you never have to buy the study, read the whole journal to see what they did exactly. We'll just go off the information given, unless you find that study really interesting and you just want to research it for your own curiosity's sake. So when this happens, if we have no information on randomization, this is all we're expected to say. We're just discussing what we know about the conditions, and what we know is it's an unknown on part two for randomization. Nothing further could really be said about that. Does that make sense to folks on the challenges on this one? Okay, now 10% condition we can say a little bit more on. What we do is we take 10 times the sample size, so take 10 times n. That's going to be 10 times 339, which equals 3,339 infants. And we have to do something about the context and decide if this is less than the population size n, we meet the 10% condition. But if this was some really rural town in, say, Tennessee, there's plenty of them where population size is like 200 from 1980, or excuse me, like 1920 to 2025, this would be really bad if that's our population. But if we're talking about infants, probably our assumption is we're talking about infants in a country or somewhere in a large county, something along those lines. I think you can kind of assume by this problem, there's a lot of infants that really are we're discussing. And we could say here, this is less than the population size n of all infants and so the condition is met. And what's kind of cool and rare about this problem is because this study was real, it really happened in 1974, you could look into that. The population is pretty big, 736,000. But we did that just for the sake of it's fun to nail something down at least once in these kind of problems. It's not something you're required to do for these kind of contexts. So it being infants alone assumes, kind of implies as a default, the population is probably pretty large, larger than this value right here. So we argued this part right here, and we said the condition is met. Any questions, folks, about that tricky 10% condition? Yeah. Exactly, yeah. So what we said here is less than the population size n. That was this part right here, which is really what's said right here, doesn't exceed 10% of the population. And that whole statement is this in inequality form. The sample size n of 339 infants does not exceed or is less than 10% of the population size is what that statement looks like. But just to make this a little bit more concrete as a number, we did it this way, 10 times n. So yeah, exactly right. We argue that that number has to be less than the whole population size for this condition to pass. Any questions about that so far? Okay, it's definitely kind of a tricky problem. Thanks for the questions about it so far. This is one way we can argue about this. The reason I kind of like this as well is because if you were to do the 10% condition verbatim as it's written down on paper, you would have to do this. Go 339, divide by the actual population size, which means you need a number, right, at that point. So divide by 736,220 times 100, so it's a percentage. It comes out at 0.04 of 1%. And so that means it would satisfy the 10% condition quite well. But you would have to have a good number for the population size. So to use this line just as it's written, you need to have a denominator. Or you can just multiply the numerator times 10 and just reason, is that plausibly smaller than the population size? Now we didn't necessarily have to have a number here. We're just thinking about the context. Is that number of infants plausibly smaller than all of the infants in 1974 in this particular country? That seems very plausible if you're talking about infants. There's probably loads of them. In fact, if you look into it further, hundreds of thousands of them is what we would have gotten.
Google said there's 3 million.
3 million infants. Oh man, I was really off. Well, you know, I was close to a million. 13.1. I wonder where I went wrong. Something in there. Yeah. So maybe something else was going on. Was it giving, by its definition of infants, less than 1 year old?
No, I just Googled number of births in Great Britain in 1974.
Oh, so yeah, that's the same kind of number that I'm going for right here. So yeah, my crude estimate isn't exactly what happened. Maybe 1974 was a good year. Who knows what happened in that year? Going by just the birth rate, you get a kind of a really bad approximation. But yeah, thanks for looking into that. Let's put that into the notes because that's pretty cool in a way. What was the figure?
3.1 million.
3.4?
3.1.
3.1 million is the actual result.
They get, and it's at any age, but it's dangerous for infants younger than 6 months. So they either get the vaccine 2 months of age, 4 months of age, or 6 months of age. They can get it like 15 months to 6 years old.
Gotcha.
Those beginning.
So that makes sense if we're thinking a year old or less. That actually fits the problem. And by the way, I've actually looked into, because I was curious about this, what does the whooping cough actually look like from someone suffering from that? I'm almost 100% sure. Don't Google this. This is not for the weak of heart. But I'm almost 100% sure these adverse reactions were like a walk in the park compared to the actual illness of whooping cough. But yeah, that's an awesome takeaway. Thanks for researching it even further. It's kind of the fun thing about these problems is the more interested you are in it, the more you can kind of figure out and suss out about these kinds of things. But if it was an exam question, then we don't have Google and we'd have to think in kind of these terms. This is probably a pretty small sample. In fact, very small relative to 3.1 million. Well, other questions at the moment with conditions? Oh, I don't think we're done with conditions. Let's do the last part, part 4, the good old success failure condition. This part is important as well because the way we do it in this example is different from the very first example. The very first example straight out, well, in a roundabout way, told us the number of successes, which would have given us the number of failures. But this problem is different. They just gave us the sample size and they gave us the sample proportion of successes. So in this problem, we really would want to use those two formulas down below here. So for the success failure condition, we can say the number of successes is take the sample size n times the sample's proportion of successes. Let's scroll up and use that part right there. So this is going to be equal to 339 for the sample size n multiplied by 0.2035. So that's the p hat part from there. You try to show both parts at once. And when you put this in the calculator, something weird definitely happens, but this is normal. Take 339, multiply this by 0.2035, and we get that number. Let's think about the context though. This is the number of successes in the sample through that formula down there, but a success is relative to an infant having an adverse reaction, which would say there was 68.98 adverse reactions, or somehow we have 68.98 infants that had an adverse reaction. That doesn't fit the context, but this is something that happens because when you calculate p hat, sometimes you round.
Well,
Yeah. So we rounded on this thing to 4 decimal places. The percentage was also rounded to 2 decimal places here. And because of rounding, sometimes these don't come out exactly right. Yet the answer here is an integer. What would you say is the best number to give to this? The number of successes. We can't give 68.98. So what would be the real best answer we could give? Yeah, we just round up to the nearest integer, the nearest whole number. So if this happens in the calculator, you didn't make a mistake. It's just that this figure wasn't fully accurate. There's more decimal places they could have given, but they rounded on the percentage. And so when we use the rounded value as a proportion, we get strange looking numbers. So let's just put down what the number is closest to, 69. So if you have 69 successes, you can use this formula down below to calculate the number of failures. But we mentioned before, thinking about this problem, you might know a shortcut already. The number of failures is n minus the number of successes, 69, which is 339 minus 69, which is 270. So that's a great way to reason. If you use this formula down below, you would take n, 339, times q hat. That's not my favorite symbol. You have to always remember q hat is 1 minus p hat. So you'll go 1 minus, put in the value for p hat, 0.2035, and you get 270 rounded to the nearest integer. So 270 failures, 69 successes. I like this way because you're less likely to make a mistake. And it makes sense from the point of view, if you have a sample size, everyone in the sample is either a success or a failure. So once you find the successes, just subtract it off from the sample. This is automatically the number of failures. What do we have to check? That they're both greater than or equal to 10. Let's put those inequalities there. Even though it looks kind of funny, it's just a reminder. This is the benchmark that we had to hit. 69 is definitely greater than or equal to 10, so it's 270. And so, since both of those are satisfied, the sample size is large enough. This now means if we look into the sampling distribution of p hat, those were those normal curves, we're going to get a very symmetric shape that really looks like it came from a normal distribution. In other words, this was the condition that has to be met for the central limit theorem to be effective as well. Well, that's three conditions. It's not all four. Independence is up to how they actually collected the data. Again, the way they treat the sample is important because if they put all 339 infants in some kind of, say, wide open space, but all the infants are together, you know if one infant is having an adverse reaction and starts to scream and freak out a little bit, probably all the infants around it are probably going to have a bad time as well, and our data is probably not going to be collected accurately. Independence really could fail if this isn't done just right, but I bet you that they were really careful with how they collected this data. These infants were isolated from each other, probably just kept in the home of the family, and there's just one child getting the injection. That kind of thing happened. We can't assess any of that because we didn't really conduct the study ourselves. So we're just trusting they did that one part right. We can give an overall conclusion. We can say here, overall, the conditions are met. They're tough to check. There's lots, again, you can say about certain parts, like the 10% condition is a tough one to check as well. We'll see a lot of different kinds of scenarios in the homework for MyLab statistics. And when we release a quiz on this, we'll do another version. So we'll see the context where it's pretty easy to determine that this condition is really met. You'll see a couple borderline cases as well, where it's a lot trickier to determine it. But we did it, folks. That's finally checking all of the conditions, not skipping a single one. And just for the sake of extra practice, one more time, let's calculate the standard error. Any last questions at all, folks, thinking about this problem or additional comments? That was pretty cool information there about the actual births in that year.
That 20.35%, that would be a statistic, right?
Yeah, absolutely.
That describes the sample.
Exactly. When it said reactions were noted in that percentage of the infants, they're talking about these ones here, but that was the sample itself that was provided. So absolutely, this one would have been the statistic. Let's write that in. This describes the sample. Which means it's a statistic. Other questions or comments so far? Okay, that's a good comment and observation to make about that, because one thing that we didn't write down on paper is what is the actual parameter. But we're going to actually study this problem further. This is going to come back in section 13.3. We'll give the full-on confidence interval for this one. So this is like the first half of the analysis. Are the conditions met? It looks like they are overall. And the very next section, we'll do the complete analysis on these data here. To get to that complete analysis, you still have to calculate the standard error. This is one big part of the confidence interval procedure. So let's practice this one more time just to get some extra practice in. We'll calculate standard error of p hat. Strategy is to now just write in the formula. It's p hat times 1 minus p hat divided by sample size n. So this then turns into square root of, and the p hat value is up here. We also stated it down below right here, a little bit easier to see. Let me just recopy it for emphasis. 0.2035, I think our bar should be just a little bit longer. So go 0.2035. 1 minus 0.2035. Divide by the sample size. And just to double check, sample size is 339 in this problem. And we get the standard error. So coming back here, hit second x squared button for the square root, 0.2035 open, and then don't forget to close a parenthesis for 1 minus 0.2035 divide by 339. So I got a standard error to 4 decimal places of 0.218. Looks like this rounds to a point, I said that weird, 0.0219. So approximately 0.0219 altogether. But we did it, folks. This is pretty much the end of the analysis on this one. I did put one additional part on here. It just says example. It's something we did before in the last section notes, but it's just a way to kind of, once again, think about how does this all come together? Why did we care so much about checking all of those conditions? And it took a lot of time, took a lot of effort in thinking about it. There's got to be a reason, and the reason is because of this next part. Let's make this the last part of the class today. Let's put this all together and do one additional thing. If you've got the standard error, you can now say the following. We have, because I already had that color there, we have that the parameter P, this is the population proportion of successes. In other words, this part is the parameter. It's unknown, but P is approximately equal to P hat, which is 0.2035. So we think that in the population of all infants in Great Britain, 1974, about 20% of them, a little bit above, had an adverse reaction. But that statement isn't complete until we also bring in the margin of error. The 68, 95, 99.7 rule does that for us. And so this is another look at that concept. Let's import this in from the last time we thought about this idea. And we can do this because if the conditions are met, the central limit theorem tells us we are modeled well by the normal distribution. And this rule is followed by the normal distribution. So we can now say an approximate (95% confidence interval). This is what the next section is all about. For the thing we're estimating, the confidence interval for P, this is the proportion of all infants in Great Britain that had an adverse reaction, is P hat, add or subtract. We look up this number. If we're doing a 95% confidence interval, the number we're using is approximately 2. And we'll put a better number down like we mentioned. We multiply that by the standard error P hat. That's the number right above that we just calculated. So that's the rule being used. And now we can compute this. This is going to be equal to value for P hat. That was the 0.2035. Add or subtract that number 2 again. Times the standard error, that's the 0.0219. And just to tie together this concept, this part right here, 2 times 0.0219, is the margin of error. This is the error making this estimate right here. Estimate the unknown parameter with the statistic. Now let's put this down below and start calculating. So when we use this confidence interval, here's what happens. The parameter P is the thing being estimated. It goes in the middle of this triple-sided inequality. In the calculator, we run this whole line with a negative sign first to get the left side. So 0.2035 minus 2 times 0.0219. So this is the low end of adverse reactions, about 16%. We got 0.1597. And then standard trick in the calculator is to up arrow, hit enter to copy that down and change this to a plus. On the bad end, we're close to 25% of infants having an adverse reaction. So 0.2473. So this is what the 68 to 95, 99.7 rule gives for us. It's a very crude approximation of the confidence interval. And the whole job of the next section is just to do a little bit better. But this is what they would have done in that Lancet journal. They are estimating the unknown parameter, the population proportion of successes, and they would have gotten numbers a little bit different, but pretty close to what we just got. And it tells a different story. You can't just say 20%. That's the center, that's the average of the sampling distribution. The full story involves the standard deviation. That's the approximate to the standard deviation, we call the standard error. And it gives us the margin of error of making our estimate. So it's a very different picture. In Great Britain in 1974, all infants that had an adverse reaction was about 16 up to about 25% of all the infants in that country at the time. So depending on what the study was really trying to do, they might have had more to say, but who knows what the adverse reaction really counted for. That could have been from things that might have been somewhat minor to maybe someone had to go to an emergency care unit or whatever the equivalent is in Great Britain, 1974. We don't know too much unless we read that whole study and see everything that went on. It's probably a pretty long one to read. But any last questions at all, folks, on this major statistical inference result? Okay, all the condition checking did for us is give us a level of reliability that this statement, that it's true, sure it's approximate, but it really is the unknown constraint between these two values. Next section is going to resolve what do we mean by confidence interval really, and how do we make it more accurate? So those are our major things, and we'll do 3 different examples, start to finish, on these same kind of problems. But have a great night, folks. If you have any other questions, I'll be happy to help out. Otherwise, we'll be in section 13.3 on next Monday. Oh, and have a fun Halloween. Try not to do anything too sketchy or dangerous, and stay safe. Have fun.
Did you remember the notes that we ended last time in class?
Yeah.
We got to that.
Yeah, that's right. I have it, I think, pulled up right here as well.
So right here, see my notes?
Hang on, there we go.
Yeah. Where did these numbers come from? Margin of error.
So that was the 2 times the 3.013, and
Uh-huh.
that's the same as this 2 times 0.0219 and this problem down below. So the margin of error is always the number times the standard error.
Okay, so you would just calculate that and then you would plus or minus it to that number.
Exactly. We
Okay.
did it kind of just all at once
I
in the
just-
calculator.
I just seen that from my notes from last time.
Gotcha.
Thank you.
Yep, you bet. And thanks for the questions and additional research on that last problem on the infants in Great Britain. That's kind of fun.
Yeah. Cool. Google powerful resource.
It is, it is. I used it this morning, but I used it in a different kind of way to get a different result, it turns out.
Makes you wonder though, right? Like, if that's the population and that's their birth rate, it's like, that's pretty, those are some big ops, you know?
Yeah,
So it makes
and
you-
that's a lot of kids for the population size. You take 56.2 divide, or let's do it differently. If you take 3.1 divide by 56.2, it says about 5% of the population was kids that were less than a year old. That's a lot of kids. They had a crazy year.
I got one more question for you.
Sure.
I'm here. We're here.
On quiz 8,
Yeah,
I feel like, I could be tripping, I feel like the answers for, is this an example of an observational study or experiment? Down, is very similar to the answer for E.
yeah,
Is it appropriate for the researchers to arrive at conclusion that the herbal supplement caused an increase in memory test scores?
yeah, they go together. So your answer to this depends on what you set up here.
Yeah.
Because if you said it's an experiment, then you would say, yes, it's appropriate. Experiments establish cause and effect. But if you said it's an observational study, in no way is it appropriate. That's
Okay.
just something we saw in the data. There's no cause and effect at all.
Perfect. Yeah, I just wanted to make sure, because I was like, yeah, it's the same.
Yeah,
Can I hand that in to you
yep,
now?
you bet. Thanks.
Thank you. Do anything, do you have kids or anything?
No, I don't, just some dogs.
They like Halloween?
You know, I have a big yellow lab that's mixed with pit bull, and she is the most skittish dog ever. She hates the doorbell. If she sees leaves blowing, that she barks at them. So she just hangs out in the back room whenever something like this is going on.
Okay, probably doesn't like Fourth of July either. huh?
No. We give her medication from the vet, trazodone, to just give her a bit of a nap whenever that's going on.
Let her knock out.
Yeah. It's kind of funny seeing a big dog like that just can't handle anything in life.
Yeah, my mom had 2 Newfoundlands and one of them's like that.
A Newfoundland, what are those?
You'll have to. They're like the rescue dogs from Canada.
Oh, yeah, I know what those are,
They're
yeah.
like the big fluffy
Yeah,
Newfies is what they're called.
I see.
Yeah, they're big, they're like 120 pounds,
That's awesome.
they're big, 50. Have a good weekend, man.
You too, take care.